quantum algorithms. Of those, one of them is nuclear magnetic resonance. We have been practicing nuclear magnetic resonance for the purpose of getting structures of proteins by NMR. When the proteins are in solution and rotating very fast, and we use nuclear magnetic resonance methods to get those structures of molecules by NMR. And for that purpose, a lot of funding has come, and we have one of the best equipped NMR laboratory in Indian science in the NMR Research Center. And I invite you to visit that place whenever you are in that area. And using those machines, spectrometers with high field magnets, very high homogeneity, the homogeneity of the magnetic field and the stability of the magnetic field that we have for the protein structure determination is 1 part in 10 to the power 9. And that is key to quantum computing as well, because then we can differentiate between the various states of the Hilbert space. And that's why we are able to do it using these methods. Okay, I'm now getting into what is NMR computer. I'll come to that later. First, after having done initial work in developing number of qubits by NMR, implementing logic gates, implementing algorithms, we have now started a program of how to implement games by NMR. Of course, theoretically, this is a very well established field, and so what we are doing is we are just confirming that we can do it by a method of NMR. The game theory itself is an interesting area of research in mathematics, especially in mathematics, and it's a very initially was put up in this book by Neumann and Morgeson. Of course, John Nash gave the idea of equilibrium, which is now known as Nash equilibrium, which is a very important aspect in game theory. He won the Nobel Prize, very celebrated person with a beautiful mind, and the book on beautiful mind. Robert Aumann gave the idea of evolutionary games as versus static games, and he also won a Nobel Prize in 2005. You can see that these are actually mathematicians, but they won Nobel Prizes in economics because the game theory has large implications in various areas of science besides mathematics. Of course, it develops the game theory. Physicists are very interested in it, but it has implications in foreign policy, economics, social sciences, communication theory, and especially in communication theory, market strategies. That is where money can be made, and even biological processes, of course, it's obvious. There are some simple examples of some simple games that we can implement easily, and I just mentioned a few of them and then show you 2 of them. Prisoner's dilemma game, and this now the 2 people are caught stealing something, and they're separately asked as to whether you did this job or not, and there are cooperativities in their answers which can lead to maximum or minimum prison term. Williams game is this game that I will talk about now, that Alice tries to find out the number that Bob has thought of. And this is a very interesting game you can play with children. Battle of Sexes, of course, men and women have different choices. They like to do different things, and this is always gets into argument, and what is the best way to avoid argument. Dilemma game is a 3-player game to decide whether the place of visit, I will mention this in some detail, so I need not tell you this, and the production optimization depending on market strategy. So we have actually implemented by NMR these 3 games using 3-qubit systems. I will only talk about the 2 of them right now because of lack of time. Okay, let's start the OLMS game. The OLMS game is a 2-player game, 2 parties, say A and B. Bob thinks of a number, say between 0 and 2 to the power -1, and Alice tries to find the number, minimum number of queries. And she will ask the question to Bob, and he will give an answer in yes and no. And in classically, it requires n queries to find that number. And if you do a quantum case, use the idea of coherent superposition, so well enunciated by Grover, you can do that in a single query. And that makes it quantum case very interesting. So the classical game is following game. So let's take a 7-qubit number, and this Bob thinks of number, say 26. Okay, and so the LS asks, is the number, you take it into half, asks whether it's number is less than 64, and Bob just says yes. So you put a 0. Okay, less than 32, yes, another 0. Less than 16, yeah, no, put a 1, and so on. And in 7 queries, then you can guess the number. Okay, so this is a well-known game which everybody can play. Now, in quantum version of those game, you have to do a trick. Basically, the trick is that you create coherent superposition states. And there are 2 registers, register consisting of n qubits, and Bob register, which consists of 1 qubit. Alice makes a superposition of all the qubits. Bob performs a unitary transform, which actually contains the number that he has thought, but Alice doesn't have access to it. It's exactly like inversion problem. Okay, but then Alice again makes a measurement by interfering the qubits, and in a single query, able to find the number. Actually, this problem is very close to Joyce-Joshua algorithm, and we actually use Joyce-Joshua algorithm for doing this process here. And so, in a 3-qubit case, we initialize the states of the Alice, register A and B is in state 1. Alice creates equal superposition, and Bob thinks of a number, let's say 0, 1, and then performs a unity transform. The unity transform is indicated here. You have to do X with A mod A. If you go through this algebra, you get this, and when you have this, Y can be either plus or minus depending upon this answer. Okay, and then you apply a unity transform the state, and then if this state is Bob's state is in state 1, then you get a minus. If it is in a 0, you get a plus. Okay, and after that, the Alice performs a superposition again, and then the final number is here. For example, in this case, Bob had thought of number 0, 1, and this answer is coded in 0, 1 then. It's a 2-qubit number. Okay. Now I've shown the NMR implementation of this game. By using NMR, we do this. And the steps involved are, first you have to create a pure state. And in NMR, we cannot create pure state. What we do is we create pseudopure states, and I will show you what the pseudopure states are. Then you can apply Hadamard gate. Hadamard gate is, like Grover mentioned, is a superposition gate, a unity transform of Bob, and the application of another Hadamard gate by Alice, and then the measurement. So these are the steps involved in getting the number. See, when I'm showing this for a very small number, it looks trivial. But if you have a large number, then where you see the power. But for doing that, we need a large qubit size. We don't have that yet. The largest qubit we have got is 8 in my lab and 12 in the rest of the world by NMR. The other methods have even less qubits. So pure states. Okay, let me spend a couple of minutes about what is a pure state and what is a pseudo-pure state. Because in NMR we can only implement pseudo-pure states. And so in some ways what we are doing is implementing the pseudo algorithms. Okay, all members in a definite known state. Okay, so in NMR we have a state, the nuclear spin is either parallel to the field or anti-parallel to the field, and we can put them in coherent superposition on the ensemble average. Okay, this is the key to NMR, that we can do everything in the ensemble average. And so we take a density matrix in the pure state, it looks like this, and the properties of pure state, the density matrix pure is equal to the square of the density matrix pure, and the trace is idempotent. Okay, so this is where things break down in NMR. So if you have any deviation from a pure state is a mixed state, and trace rho square mix is less than 1. For example, let's take an equilibrium density matrix and the off-diagonal elements have become 0. This is what happens when decoherence takes place, for example. Then we have populations of various levels. And then if you calculate the trace rho mean square, it is less than 1. To obtain a pure state in this equilibrium system, what we will have to do is we will have to channelize all the population in one of the states, so that all others are 0 except 1. And in this case, this trace rho square will become equal to 1. Okay? All right? And that will be a pure state. So basically, a pure state will be an ensemble pure state, will be one in which we can channelize all the populations in one state. Need not be ground state, but it can be a ground state, for example. And then the question is, and this is a mixed state. When thermal equilibrium normal population distribution is a mixed state. So how to obtain a definite initial state? Of course, this requires unrealistic experimental conditions to do. We cannot do this. What we do is, in NMR, we expand the density matrix that we work with in what we call as high field and high temperature approximation, or basically keep the linear term in the expansion. And then we express this as a unit matrix plus a deviation matrix. What we can do in NMR is put the deviation, this unit matrix actually commutes with all unity transforms. Doesn't do anything, remains as it is. Okay? And so we can sort of ignore it. All right? And then we can put this deviation density matrix into pure state. And we call this as a pseudo-pure state. In fact, it mimics, what we call is it mimics a pure state. So basically what we are doing is that we then create such a state in which we have a unit matrix with a uniform background and deviation part in one of the states. Okay? And so this is expressed, and thus we say that the pseudo-pure state mimics a pure state. For example, for a two-spin system, which are coupled to each other, there are 4 states. Both the spins are up. That's 0, 0. One spin is up, one is down. There's 1, 0 or 0, 1. Or both are down, 1, 1. So these are the 4 states of a two-spin system. Okay. In equilibrium, they obey Boltzmann distribution population. Actually, I should write here a million plus 1, a million, and a million minus 1. Okay. That's the Boltzmann distribution. And I am ignoring the million. In fact, in all spectroscopy, we don't get any signal from the million. The million remains in the background. We only get signal from the difference of populations. And that's what gives you signal P1 minus P2 square. P1 minus P2 gives you the signal. Okay? And so in any case, the signal that we see in spectroscopy is only dependent upon the deviation part. And it's the deviation part that we play with now. And so it is possible then to put it into this status. Okay, we have to add a little bit of the equilibrium, a little bit of the I part into it to make it look like this. Otherwise, this is not traceless, this is traceless. But that's just a matter of semantics. There are many methods that have been suggested for creating pseudo-pure states in NMR. Spatial averaging, temporal averaging, logical labeling, using cat states, pure or pseudo-pure state, and especially average logical labeling state. This is also done by my former student Mahesh when he was a student there with me. And then basically we sell this by saying that, except this one, all these scale badly with larger number of qubits. The number of operations goes up exponentially for all these things, but not for this one, provided you do one of the operations in transition selective manner. Okay, so we have in this work we will use a spatial averaging method, which has been given by David Corey. For other methods we have used this. Other things we have used this method. Okay, and so suppose we have a three qubit system. How do we prepare a pseudo-pure state? We start from an equilibrium density matrix, which is given by this. And this is the density matrix corresponding to a pseudo-pure state. And so we perform certain operations which these spins have coupling between them. And we do a coupling evolution. By coupling evolution, we can then create different states of the spins. And finally, the result will come out here. I'll show you with an example. Okay, here is of course you are working on two of the qubits. You start 1-3 evolution, 1-2 evolution, and 2-3 evolution, and basically this will lead to this state. Okay. This we have done now, experimentally demonstrated in a 3-qubit system. Now I can introduce qubits here now. For example, if we take this molecule, there are 10 to the power 20 such molecules in my sample tube. We cannot address each spin individually. What we do, we address them in frequency space, NMR frequency space. For example, if these 3 fluorines have 3 different Larmor frequencies, then all the 10 to the power 20 fluorines which are resonating at this frequency are treated as 1 qubit. Those resonating at this frequency as another qubit, and this another qubit. So there are 3 Larmor frequencies, there are 3 qubits. All the fluorine, 10 to the power 20 fluorines resonating at one particular frequency collectively are treated as 1 qubit. Okay. And then we need a coupling which can do information transfer, and that coupling is provided in NMR by indirect spin-spin coupling. The nuclear spin interacts with the electron of its own, which then interacts with the electron of the neighboring nucleus in the molecule, and which interacts with its own spin, and therefore we have spin-spin coupling. The spin-spin couplings are of this order, and the gate time in NMR is inverse of the J coupling. Okay, and so therefore it's a good idea to have a larger coupling. The coherence time versus gate time ratio in all the 4 or 5 technologies that we know at the moment are approximately the same, 10 to the power 3. Okay, so, but NMR systems have very long coherence time, but very short coupling. Okay, so the gate time again ratio is 3. So in fact, NMR systems are easy to work because our coherence times are long, of the order of hundreds of milliseconds, and that's not there in any other technique. But their gate times are short, so there are positive and negative aspects of it. All right, as a result of this, if you take the simple fluorine NMR spectrum of this, for each qubit we are splitting this frequency splits by coupling to this into 2 lines, and by coupling to this, each is split again into 2 lines, so we get a 4-line spectrum. Each of these lines correspond to the states or other 2 qubits, state 0, 0, 0, 1, 1, 0. So this is the transitions of this spin in which the other spins are state 0, 0, 0, 1, 1, 0, and 1, 1. Okay, and like that, this is the equilibrium spectrum of this. For a chemist, this is trivial. Okay, but then we use this as a 3-qubit system. All right, and then we prepare the pseudopure state according to the recipe that I had given earlier by this method. Okay, from equilibrium, and we get this result. Look at the result. What we have done is we basically populated only this level 0, 0, 1. So we will have the second qubit in the positive, the first qubit in the positive, and the third qubit in the negative transition. And all other transitions are 0 because all other states have no population or equal population. Okay, and that exactly is actually the result, experimental result. So this is the experimental proof that we have prepared the system in a pseudopure state, corresponding to the state 0, 0, 1. Okay, and now we perform A equal superposition. The equal superposition can be performed if you want exactly the same Hadamard gate by a pi/2 pulse followed by a pi pulse, or by a equivalent pseudo Hadamard gate which just needs 1 pi/2 pulse. We actually do this because this differs from this only in a phase factor, overall phase factor, which we don't care. And then you perform a unitary transform of the Bob, which is the number that he has thought of. Okay, and then the control knot operation 2-3 is performed, and so the 2-3 control knot operation basically codes that he has thought of the number 0, 1. All right, and if he has thought of some other number 1, 3, for example, if the number was 2, then he would have performed control 1, 3, and things like that. So the pulse program for doing this is given here. It starts with a NOT gate to correct the phase. Then we perform a pseudo Hadamard gate by applying a 90-degree pulse in all of these qubits. then apply a C, not 2-3 gate here, and I don't want to go through the details of this operation, then another pseudo Hamarth, and then we have actually put these slightly carefully together so that some of these pulses cancel out. For example, the Y bar and Y pulse cancels out, and X bar and X pulse cancels out, and these two pulses cancel out, and we get a simplified pulse scheme, and we then implement this particular pulse scheme rather than the complicated pulse scheme. Okay, and then we get the result. The result of the control node 2-3 operation was that this operation is transferred from here to here, which in the first 2 qubits codes the number that Bob had thought of. So now the fact that we have got this is exemplified with this spectrum, that we have this first qubit in positive number, the second qubit in negative, and the third qubit also negative. So you see this, and no coherences. The coherences are almost absent. This is the error in our experiment. Okay, and so we have in populations we have error of the order of 5%. In coherences we have error of 10% because of decoherence problem in the whole system. This is the entire density matrix imaged tomography, we call it, and there I have shown only few elements here. Here all the elements, and so the question is, the game over? Yes, as far as this game is over, except that now we can also look at another game. Suppose Bob is allowed to lie L number of times. The classical complexity again goes up, even the quantum complexity goes up, but not as fast. We have not yet implemented this. We are still working on it. We need large number of qubits for doing this. Well, the games with corrupt source qubits, the 3-qubit dilemma game with corrupt source is what I am going to show you next. This is a very interesting problem that there is a very famous bar in Santa Fe called El Ferral bar. It has a limited seating capacity. A large number of people want to go there, and you have to decide whether to go there or not. Okay, and you decide depending upon what is happening in the. If you go there and you don't find a seat, you're very disappointed. If you don't decide not to go and there were seats there, you again get disappointed. Okay, so how to optimize this idea? To go or not to go is the question. All right, and it's a very, very interesting game. This is, I'm going to show you a 3-player game, and this is the payoff table. Okay, in the state, no one goes to the bar, so the answer is 0, 0, 0. No one gains and loses anything. So the payoff for that is given by this. This is by these people. Okay, then if only one player goes to the bar, there can be 3 possibilities, and one of the persons who has gone is happy, but unhappy to some other extent that there are nobody else there to him talk to. So there is a certain payoff. His payoff is good. The other payoff is minus. The 2 players go to the bar is the optimum. So you have the 3 again possibilities. Which 2 players go, they are all happy. This is the highest payoff in the system. But if all of them try to go, then one of them doesn't find a seat, and then the payoff is lower. So this is the classical payoff table. Now this is the payoff table without corruption. Okay, and so basically input is 0, 0. The moves are do nothing. Flip one bit, and to go to the bar with probability half, to flip one state with probability half. Okay, the dominant strategy is the classical case in which all of the 3 players decide to go with, and the average payoff per player in this strategy is 2. With the corruption, this payoff comes down to 0 in the classical case. Okay, but in quantum case, the situation is different. The players share, in the classical case, players share no correlation. Here the players share quantum correlation, entanglement among themselves. The J gate, as we will describe, introduces entanglement among the players. The classical game is a subset of the quantum game. The best classical strategy is all the players flipping their own bits, and this yields a payoff of 2 per player. The best quantum strategy is one player flips his bit, the second player flips with the probability half, and the third player does not flip. And this yields a payoff of highest payoff. Okay, with the corruption, the situation changes. Okay, and here is the payoff table. There are 10 classes of with corruption that have been introduced, where the P is the probability of not flipping, the number of players who have chosen the particular strategy. The class 8 has the optimum strategy. Okay, with no corruption, this has the highest payoff. It's higher than the classical payoff, but with corruption, this payoff becomes lower than the classical payoff. Class 7 has the same payoff, but it's not fair to all players. So the 8th is the best strategy. The bit is either it is going through the noisy channel, and it's not, can't say it was how bad it is. Okay. So quantum game has a higher payoff as compared to the classical game, but the quantum advantage disappears if the source is corrupt. Okay, and I'll show you in the table finally what the answer is. Okay, we have implemented this now in case of again another 3-qubit system. This is all heteronuclei as we call it. There are different nuclei with different nuclear gyromagnetic ratio. The advantage here is that we can apply pulses to the spins in a much shorter time, because we can apply hard pulses. When there are 3 fluorines, we have to apply frequency selective pulses, and they are slightly longer. But here we can apply much shorter pulses because the frequency difference is in megahertz rather than kilohertz. Okay, and so of course there are coupling constants there, and this exactly looks like them. This way, this spectrum looks very similar to the fluorine case, but here this is proton, fluorine, and carbon spectrum. We need 3 RF channels to do this experiment. The NMR implementation is that we create a pseudo-pure state. The daemon introduces corruption in the source. So this is how we do it experimentally. We deliberately introduce a daemon, okay, and check on the result. And then we have an entangling gate. We have moves here, a disentangling gate, and measurement. Lots of pulse sequences. So here, well, these are matter of details and algebra. We perform these unitary transforms on these spins, and you can check on them, followed by this, and then we get a pseudo-pure state. This is exactly the same thing that we did earlier, and I'll just show it again. Okay, and then here is the result that we have now prepared a 0, 0, 0 pseudo-pure state, and therefore all the 3 transitions that we see are with positive intensity, and here are our errors, okay, in the pseudo-pure state preparation. Okay, so these are experimental results. All right, and then we apply a daemon. Basically, the daemon is given by this single pulse, which creates a mixture of these 2 states with a slight mixture into 1, 0, 0, and then we spread it over and create entanglement on the 2nd and 3rd qubit. So basically, we are creating this state with corruption. Okay, and epsilon is the amount of corruption that we have introduced into the system. And this is the entangling gate that we need to do. And basically, if you go to the result about this, basically evolves the system under this system Hamiltonian, and then the moves are do not flip the state, identity operator, flip one state, not operation, a pi pulse, and flip one state with probability half, we apply a pi by 2 pulse. Okay, and then we apply a disentangling gate, which is a conjugate transport to the entangling gate, and in NMR it is applied by changing the phases of all the pi by 2 pulses of the entangling gate by pi 180 degree. Then we look at the result and calculate the payoff. Final populations are measured. The diagonal elements of the output density matrix are reconstructed from the population spectra, and the payoff is calculated from the diagonal elements using this payoff formula. And here is the result. Actually, this is the result corresponding to move number 8. This is case number 8. Okay, case number 8 here. And this is the theoretical expected result. This is our experimental expected result that we have got. This is for input 0, 0, 0, and this for the input fully corrupt case 1, 1, 1. and we expect this result, and we got this result. So here is the case where I just want to show you that the result is that with no corruption, epsilon equal to 0, we are expected to get population in this level and then this level. So we will get two negative peaks in one qubit, in qubit number 1, and in qubit number 2, in qubit number 2, and here it is, and we have a positive peak and a negative peak in qubit number 1, and we have one positive, one negative in qubit number 3. So this is the situation with no corruption. With full corruption, we have population in 0, 0, 1 and 1, 0, 0, and this spectrum then corresponds to what is expected. Okay, and this is the diagram which explains how we get this. And these are for intermediate corruptions. And from this, we can calculate the payoff table. In fact, the student has done experiments with all the cases, okay, with no input, with no corruption and full corruption. And so these are the theoretical results and the experimental results, and these are then plotted into this final diagram. Here is the summary. This is the result for class 8 actually, that classically with zero corruption, the payoff is 2, and it goes down to 0 with full corruption. Quantum mechanically, the payoff starts high and it crosses the classical case and goes much lower than the classical result. And so this is the theoretically expected result in this case, and dots are our experimental data points. So we basically have implemented the dilemma game, 3-player dilemma game by NMR using a 3-qubit system. The conclusions are the 3-player has been implemented, the game with corrupt source has also been studied, and we have still to do evolutionary version of the game.
Thank the speaker for a very nice talk, and we have time for a few questions. Well, I have one question.
Yep.
It's a dumb one. How do you actually do the rotation operation in the experiment?
How do we do the experiment?
Yeah.
Yeah, I realized later I should have added some more transparencies to explain the NMR part of it. Basically, what we're doing in NMR, see, in a sample tube, we have large number of spins here. We cannot address them spatially. Okay, so you can think of a scenario where you may do MRI type of a pixel applying gradients. But the problem with that situation is that we need to have coupling between the qubits. Okay, and that doesn't exist then. So we don't do special encoding. What we do is we look at NMR resonance frequencies. Okay, so all the spins which have one frequency are treated as one qubit. And other spins which are in the same molecule, which are coupled to them, but have different Larmor frequency, are treated as another qubit. So we have to find molecules in which spins have different Larmor frequencies and have coupling between them. One of this J coupling is through the bond. And this coupling goes through only, for a few bonds. And so there's a limitation that how many qubits one can get by NMR. We have been working on ideas in which how to increase this size of the NMR qubits by using dipolar couplings. Now dipolar couplings become 0 in liquid state NMR. Okay, in solid state NMR they are just too much. So what we have been doing, we have been putting molecules in liquid crystal medium where they retain only intramolecular dipolar couplings which are scaled down by the order parameter. And intermolecular dipolar couplings are 0. So we get a finite size system. But if there are spins with the nearly similar Larmor frequencies, then we get second order couplings. And so the spin is no more a qubit in that case. But what we have been trying to say is, in fact, the 8-qubit system that we have shown is that we have 8 spins coupled to each other, but the Hilbert space is 2 to the power 8, and we collectively treat all the 8 qubits together as 8-qubit system, but individual spins are no more qubits, individual qubits, and there are problems with that algorithm. Yeah.
Thank you.
So, in other words, that you can apply this game theory only to the through bond connectivities, not to the dipolar systems.
No, in dipolar systems also we can. At the moment, we only know how to do it in systems in which a spin is a qubit. In the dipole coupled spin system, we don't have spin as a qubit, but then we have access to the full Hilbert space. One of the ways to do it is what some other people are working on it, we are not working on it, is called strongly modulated pulses. So what you do is you say, this is my initial state, this is my target state, and using control theory, you design a pulse sequence which will achieve the target state. In which case, you don't need to know anything in between. Okay, and so that will achieve game in strongly coupled spin system.